Bu masih mute?
Terima kasih Bu Fenty. Assalamualaikum warahmatullahi wabarakatuh. Good afternoon everyone. First of all, I would like to say thank you to Mr. Andrew Charleson. Oh, I hope it's correct to say that, for your time and willingness to share your experience and knowledge with us. Secondly, I also want to thank to all participants, the student and lecturer who have attended this guest lecture. The mostly of student here I know is who attend this lecture is from architectural, structure, and construction. Besides, I also saw some lectures here. As you know, today we have a guest lecture from Associate Professor Andrew Carlson from Victoria University of Wellington, New Zealand. On this occasion, he will discuss the topic about system structure, structure element, and load distribution system. This topic is in line with our major, architectural structure and construction. Hopefully, this topic will provide input to all of us, especially to solve the problem discussed. May this lecture will be given beneficial to all of us. That's all from me. Time is back to moderator. Please, Bu Fenty, continue.
Baik. Ya, terima kasih Bu Dewi atas pembukaannya. Nah, sebelum kita mulai, adik-adik silakan mengganti nama username-nya. Ini agar saya mudah untuk assign ke breakout room-nya. Gantinya adalah kelas diikuti oleh kelompok. Jadi misal kelasnya A dan kelompok 1 menjadi A1. Kalau B, B1. C, C1, salah C lagi. Q1. Jadi ada A1, B1, kemudian Q1. Nah, di depan terus kemudian diikuti namanya. Ya kan sudah ada yang ganti B dan ya jangan lupa kelompoknya ya. Kemarin kan sudah disetorkan tuh nama kelompoknya. Silakan diganti, nanti akan saya assign ke breakout room karena ada kegiatan workshopnya. Jadi kalian mengerjakan bersama-sama gitu. Oke. Siap, kalau begitu ini sudah siap, semuanya sudah oke. Ya, so now today we will begin the lecture by Andrew Charleson. So I hope that you can enjoy the lecture and try to ask as many questions as possible if you don't understand, because he is the one who can explain about structure. Sometimes you are having a lot of questions about structure, so this is the time for you to ask about structure to him. So I think now I give the time to Andrew to start the presentation.
Oh.
Still mute.
Thank you very much for those very kind introductions. I'm really delighted to be able to give you people in Surabaya a lecture while I'm remaining in my home in Wellington, New Zealand. It is quite amazing. So I'm going to talk about structure this afternoon, and I want my lecture to be very, very relevant to your design project. And so I hope that in my lecture, I will really help each of you to develop the structure and design for your architectural project. And so now I'll just share my screen with you. Okay, so this is the title of my lecture, and it's going to be in two parts. In the first part of the lecture, I'm going to talk about the design that you will need for your project for gravity loads on your two-storey design project. And then after some questions and discussion. And after an opportunity for you to apply the knowledge to your design that might take up to 30 minutes, then I'm going to move on to the second part of the lecture, which is to provide you with the knowledge you need so that you can design your project to resist earthquake forces. Because the two main loads on your design are gravity loads and earthquake loads. And so if you have a good strategy for both of those, then your structure, can be quite easily accommodated into your design. So my lecture is primarily about the structure you need for your design project. But before I start, I just want you to be very clear that what I say about structure has to fit in with two other key design criteria in your project: the program of your project and your design concept or your design idea. And any structure that you show on your drawings that you design, your structure must integrate with these two criteria. In other words, your structure must support your program. It must enhance the usability of your building. It must make circulation easier. It must integrate in with your spatial planning. And secondly, the structure that you will design for your project, this structure must enhance your design concept or design idea. For example, if your design idea is about transparency, then you must not use many structural walls. If your design concept is, say, about chaos, some of you might want to design a house where the concept is chaotic. Then you must make sure that your structure also has a chaotic quality to it. And so that is really all I want to say about the architectural aspects of using structure. So once again, your structure, it must support the program or use of your design. And secondly, the structure must help express your design idea. And so you've got to take what I am saying, and you have to ask the question, how can I transform the simple structures that Andrew is talking about for my design? This is your job and your responsibility. So let me now move on to talk about the structure that you will need. And initially, as I said, I'm going to be talking about the structure to resist gravity loads. And you learnt about them in a previous lecture. The dead loads of the building, in other words, the self-weight of your design, and also the live loads, from people, from furniture, things like that come and go during the life of your building. Now, I'd just like to make you aware that there's a very good reference that is on your course reading list by Francis Ching, The Building Construction Illustrated. And so if any of you students are not feeling very confident about designing structure, then I strongly recommend you go to this reference, and I hope your library might have it as an e-book, an electronic book, hopefully. Then you can use this very, very good reference to give you increased confidence in the design of your structure. And I'm going to use just a couple of illustrations from Ching's book this afternoon. And this is one of the illustrations, because this shows two types of planar structure that we as architects use in our buildings. Now, the first type of planar structure is at the top of the diagram, and that consists of posts and beams, or columns and beams. Now, you'll see that there are three separate structures there. And if you look carefully, you'll see that they are of three different materials. The nearest columns and beam are made from wood or timber. And I don't think you will probably be designing in timber, but you can, and you might. The next post and beam structure is structural steel, and that is evident because of the I-shaped section and the I-shaped column here. And finally, we've got the structure here in reinforced concrete, a reinforced concrete column, a reinforced concrete beam. And so these structures of columns and beams, these are the most simple structures that you can use to resist gravity load in your two-story house. Now, of course, on top of each of these structures, you will need a floor slab. And I'll come to that soon. So that the beams of each of these structures, they will support the floors that you will also be designing. And so one of the very popular structural systems to resist gravity loads throughout the world is the frame system, columns and beam. And so this is a system that you may want to use in your design. It's entirely up to you. The other most popular system in the world for resisting gravity loads in buildings are load-bearing walls. And there you can see three load-bearing walls. The first wall is made out of wood. It might be called cross-laminated timber construction. And I'm not sure if that's available in Indonesia. I'm not sure. Then the next type of load-bearing wall can be of some sort of masonry. It could be a brick wall. It could be a concrete block wall. It could be, yes, any type of masonry. And finally, and the best type of load-bearing wall that we can design is in reinforced concrete. And this is a simple and basic reinforced concrete wall. And so if you, as an architect, wanted to, you could resist all your gravity loads using load-bearing walls. It is your choice. Like if, for example, your design concept was for a very introverted house, a house with many internal walls, then you could have all your vertical elements as structural walls, load-bearing walls. The choice is yours. Or you can mix these systems. Now, also from Ching, here is an example of using the columns and beams to create frames. This diagram is a little bit difficult to understand, but basically we are looking up underneath a floor slab. And so here is a column. These are the beams running between the columns. And this is the floor slab spanning between the beams. And this is an example of using these frames on a square grid. Now, often architects use square or rectangular grids to lay out their columns and beams. And usually they prefer square or rectangular grids because that makes it easiest for construction. Contractors like square or rectangular grids because it's the easiest to build. But as architectural students, you have to be critical of that because remember, you are not designing your building for the contractor. You're designing your building for your client. And therefore, the grid, it should serve your program and your design concept. And I just want to tell you that the famous Japanese architect, Toyo Ito, in one of his buildings, he used curved grid lines. Imagine that, all the grid lines were curved. And so it would have been a nightmare for the builder, but the result is an amazing piece of architecture. And so it's very important that you are not enslaved by square or rectangular grids. The previous slide was for a reinforced concrete design. This is how we would lay out the structure for a house, say a two-story house in structural steel. See, the columns are using steel sections, I sections. And between the columns, we would have this beam would be called a primary beam. And then these beams here, they are called secondary beams because they are supporting a lesser area of the floor. Like, for example, this beam here, it's supporting this much floor area, that much floor area. This beam here is supporting this much floor area. And so we call this the primary beam. And these are the secondary beams. And these secondary beams are fairly close together to support the floor system. And if we're using structural steel in a concrete on concrete steel decking, we don't want this to be more than about 2 meters. So this distance is quite short. But you can see the distance between these columns is about 6 meters. And this would be about 6 meters. So that's how we would design the gravity structure for a steel building. What about a wooden building? Well, it would look like this. We would have our wooden columns going up. We would have wooden beams supported by the columns. Then we would have timber floor joists spanning between the beams. And finally, we would have our timber flooring. In this case, the timber flooring would go this way, supported by the floor joists. So this is how we would design the framework for a timber building. Now, while I've got this slide up, I'd just like to point out to you the fact that all the columns of this two-story building, they are continuous. You know, each column starts at the foundation and then goes directly vertically up to the roof. Well, that is what you should do in your designs. In most buildings, the columns are continuous from one floor to the next. Okay, it's not such a good idea to start a column in one position and then move it to another position on the floor above. It's possible, but it's not a good idea. And maybe you might have some questions about that. So then we come to the question of how will we lay out our vertical structure, our columns. And as the designer, you have a huge range of choices. We could start by having, you can have your structure, you can have many columns closely spaced, and they can be uniformly distributed throughout the plan of the building. Like, for example, you could have closely spaced columns just running along these lines, and you could have your flooring running this way. In other words, you do not need beams running this way. Or if you wanted to, you could have your columns on a square grid like this, and you could have beams connecting each column, and these areas would be your floor slabs. These would be your floor slabs. Or you could have a system like this with your columns in the middle of your floor slabs. But that is really a very unusual system. Another option for you is to have your columns spaced further apart. And so in this design here, you've got perimeter columns around the perimeter of your building. And then in the interior, you just have one line of columns here. And so like this beam here, it has to span, you know, 2 bays from here to there. This beam, 2 bays. And so in this design, your beams have to span, well, twice as far, and therefore they are a lot deeper. They're a lot deeper. It's also possible to have beams, you know, on the diagonal. And so if you wanted to, if this pattern was really going to help you express your design concept, then you should have these diagonal beams. I mean, this is not economical, this design, but it could be exactly the right architectural solution to express your design idea. Here are my final examples or possibilities. If you wanted to, when you are designing your building, you could have all your vertical structure on the perimeter. If you wanted to, you can. And so what you would do is to have your columns just around the perimeter. And then you would have beams running across your building and maybe along your building to support your floor slabs and your interior walls. Or if you wanted to, you could have just 4 columns in your building, in your house project. Imagine that, just 4. That would be amazing. And that could be a very good idea if, for example, you were interested in maximum transparency. Or you could have 6 columns, 3 there, 3 there, connected by beams. And you would have a beam along here. This would be a cantilever to support these end beams. So this beam here is supported by this cantilever beam and this cantilever beam. Or alternatively, you could do this. You could have 4 columns and all of your beams could be cantilevered to the perimeter of your floor slabs. So I show you these slides to help you understand that you have an infinite number of possibilities. And I want you to try and choose a possibility that will enhance your design idea and support your program. I don't want you to choose a boring structural layout because good architecture is never boring. Okay? And here are some other ideas in terms of beam layout. And you can see that it's possible to have all sorts of different layouts. Like say, for example, you are designing a circular house. Well, you could have a central column and columns on the perimeter, and you could have radial beams. And so each of your floor slabs would be designed like as a triangle in plan. You'd sort of have like triangular floor slabs. And if you wanted to, there are other options for you to design your beams and columns. And so before you consider any of these, you ask yourself about what your design idea is and what your program is. Now, this is the question that is just so important for each of you, because as architects, you've got to show the beams of your building in cross-section and in elevation. And so you've got to know what the depth of your slabs and beams are. Now, architects usually go to a textbook, and in many textbooks on structures, the authors present tables like this that give architects the approximate dimensions of the. First of all, let's look at the slabs. Sorry, I've got to go back. So you need to know how deep your concrete, how thick your concrete slabs are going to be. And so if you have slabs that are cast in place, poured in place, or cast in situ, that's the reinforcing steel in the slab. If the slab is very simply supported, then the thickness of the slab is the span divided by 25. And I would suggest that is what you use in your design. Don't worry about this. It's a bit complicated. Whenever you have a floor slab, its thickness is the span divided by 25. So if you have a slab spanning 5 meters, it will be 20 centimeters thick. If you have a slab spanning 2.5 meters, it'll be 10 centimeters thick or deep. And so that is the simple rule of thumb. That is all you need to know to work out how thick your slabs are. Now, what about beams? The beam equation is a little bit more complicated, but the rule of thumb for you is this: the depth of a beam is the span divided by 15. Please write that down. The span divided by 15 is the depth of your beams for your building. So if your beam is spanning 5 meters, it needs to be 30 centimeters deep. If your beam is spanning 15 meters, it has to be 1 meter deep. And so as you think about the design of your structure, you need to be thinking about the span of your beams and how deep they will be. Obviously, you probably don't want very deep beams. And so that means you want to keep your spans, say, to less than 10 meters. like a 10-meter span, the beam has to be about 70 centimeters deep. So with those rules of thumb, you are now able to work out the thickness of your slabs and the depths of your beams for gravity loads. I just want to highlight the shading here. See this, the shading on this diagram. I'll go to this one here. That represents like the sensible limits of these beams. Like if you're designing a concrete beam, it will typically be no shorter than 5 meters, and it'll typically be no longer than 20 meters. Like, I mean, if you have a 20-meter deep beam, its depth is going to be 20 divided by 15, which is like about 130 centimeters. That's a very deep beam, isn't it? And so this table is just reminding us to be sensible. What about for floor slabs? It's telling us that for floor slabs, they shouldn't be any longer than, say, about 6 meters. Because if your floor slab is longer than about 6 meters, it becomes very thick and therefore very, very heavy and very expensive. So these are practical considerations that designers always are thinking about when they are designing their structures. Now, Fenty, that is all I'm going to say about the gravity structure for this design project.
Okay.
And so I think we thought we might have some time of questions, and then the students could maybe get a pencil and paper and just do a sketch of their building plan and just sketch roughly where they might put their columns and their beams. So it's over to you, please.
Okay, thank you, Andrew. It's time for question and answer. Bagi adik-adik yang ingin bertanya, kalau misal nggak bisa pakai bahasa Inggris, boleh diajukan pakai bahasa Indonesia, nanti saya translate. Kalau pakai bahasa Inggris langsung akan lebih baik. Jadi silahkan kalau mau ada pertanyaan bagi adik-adik, baik yang dari kelas struktur maupun yang dari luar kelas struktur tentang yang tadi itu, bagaimana cara resist to gravitational load. Ada yang ingin bertanya? Silakan raise hand.
Malu.
Iya, jangan malu-malu katanya. Silakan raise hand. Oke, Syahla. Oke, Syahla.
Yeah, Assalamualaikum warahmatullahi wabarakatuh. Thank you for the opportunity, Mrs. Fenty and Mr. Andrew. I would like to ask about the book you have suggested, the Mr. Francis book. I had read it sometimes while I was doing my task, and I'm sometimes confused about the table, how to read it, like this one, for example. But if in the book it's in the page 100 about the spanning system, so the table, the the table is like maybe I would like to
Share screen?
share screen. Yes.
Okay. Okay, I will stop Andrew's share screen, and now you can share your screen, Shahla.
Oh, yeah, thank you, ma'am. Like this one, Mr. I'm still not really understand how to read this type of table, because it will be really it will be really helpful for me to deciding about the spending maximum and the minimum distance. Yeah, that's my question. Thank you.
Okay,
Okay.
well, thank you. That's a really terrific question. Could you just show me the title of the diagram? Yeah. So this diagram gives you the approximate ranges for each of the structures. So if you look at concrete beam, if you can scroll down a bit to concrete beams, yeah, that's great. Now you'll see there that under concrete beams, you've got that grey line. That grey line, that represents the sensible limits of using concrete beams. So it's saying that if you're using concrete beams, they should be no shorter than about 5 meters, and they should be no longer than about 13 meters, you know, which is what I was saying before. So, and like take concrete slabs, say one-way slab and beam, or no, above, concrete slabs.
Atasnya?
Yeah, there, yeah, slabs there. Concrete, one-way slab and beam. Yeah, that's it. Well, you see, it typically should be in the range of about 2 meters to about 6 meters. Because if it's spanning further than that, it'll be too thick and deep and heavy. And so this is like a practical guidance for you. But this table, it only tells you what are the sensible spans. I hope there's another table that tells you what the depths need to be.
Okay, thank you, Mr. for the answer.
Okay, thank you, Shahla. Okay,
Very
next.
good question.
Yeah, next we have Ahmad. Ahmad? Faza ya? Ya, oke.
Iya.
Halo Faza.
Bisa terdengar ya, Bu?
Iya.
Okay, so yeah, thank you for the opportunity. My name is Faza, and I want to ask Associate Professor Andrew Charleson about what you said previously, that we as a designer or as an architect have our own choice or our own design of structure according to our program and our concepts or idea. You also encourage us to not always choose the generic one and to design a not boring architecture. But my question is, how do we know that our structure is okay? I mean, that our building could stand up, and without any reference. I mean, if we create our own structure arrangement, how do we know that that structure is can stand up and okay without any reference or precedence to support it? Thank you.
Okay, that's a very, very good question indeed. Well, let's just talk about gravity loads at this point. You start off by thinking about the floor slab. And so your floor slab has got to be supported by beams or load-bearing walls. And so you have to satisfy yourself that your floor slabs have got enough support underneath them. And then you've got to make sure that, and say your floor slabs are supported by beams, then you've got to be able to demonstrate that those beams can be supported by columns or load-bearing walls. And so you have to build up this structural framework that can withstand the weight of the floor and your roof slabs anywhere in the plan of your design. And I mean, as a test for you, what you can do is to make a very simple, rough cardboard model. And you can model your floor slabs by a piece of cardboard. You can model your beams with a simple bit of wood or cardboard. And then you can, press with your finger on every square meter of your floor plan to show that your structure is okay. So those are two techniques that I would suggest you consider. I mean, if your building is using a generic framing system, like straight out of Francis Ching's book, well, then you can know that system will be successful because you have obtained it from a textbook. But most of the systems in Mr. Ching's book are boring, and they are not suitable for your design idea, I'm sure. Unless your design idea is very boring, and I'm sure it is not. That's a very good question, thank you.
Oke, thank you Andrew dan terima kasih Faza. Tadi berikutnya ada Amira.
Okay, thank you, ma'am. Hello, my name is Amira. I would like to ask you about load-bearing wall made from timber and wood. Usually, we find a load-bearing wall made from reinforced concrete and masonry, not from wood. I would like to ask you about, is it not going to be too expensive? Is it, how is the strength compared to the other two? And does it really work it? Because as what I know, it needs a lot of maintenance and it's quite expensive lately. And where can we find it? Because I haven't found a load-bearing wall made from timber. That's it. Thank you.
Okay, thank you. Very nice question. Well, let me just say to you that 95% of the houses in California and in New Zealand have load-bearing timber walls. 95%. So load-bearing timber walls are very, very common in some countries. And in fact, if you look at vernacular housing in Indonesia, you will find timber load-bearing walls. Now, in my own country, like New Zealand, timber is used as load-bearing walls because it is the cheapest type of construction. And we also, we treat or we preserve the wood so that it is not attacked by insects. But in Indonesia, you've got a totally different situation, haven't you? I think your timber is probably very expensive, and it is perhaps more difficult to treat against insects. But timber load-bearing walls are very strong for low-rise construction. And so for like a two-story house, it is so easy for you to design timber load-bearing walls. And if you look at Francis Ching's book, he will give examples of timber load-bearing walls. In fact, if you Google timber load-bearing walls, you will see how we build them in America and New Zealand and other countries. Sometimes we use plywood to give them additional strength, but typically we just use lots of vertical members. So I'll just let you, do some internet searching to help you get some more answers to your very good question. Thank you.
Thank you, Andrew. Yeah, I think it is rare for you to find those kind of construction in Indonesia. But I hope that after finishing your undergraduate, maybe you can go to California or even to New Zealand to see directly how it applies in building construction. So yeah, that's the easiest way to find out. I mean, experiencing is the best lecture. So yeah, I hope that you can go to those countries to see how it applied to the building. Next, we have two more questions, I think, Andrew. There are Tony and Shafa. I think Tony, go first. Okay, Tony?
Okay, thank you. My name is Tony. And you just explained earlier about on framing system like perimeter system and radial system. My question is it good idea or good practice to combine this system? Just combine two systems, or should we just stick to one system in our entire building?
That is again a terrifically good question. I think you can mix systems. I mean, especially in a large building, say like a library building or a hospital, or even some office buildings, it is very common to have mixed systems to accommodate different spatial planning requirements. Like say, yeah, that's all I want to say. And even for a house, it's okay to have mixed systems. You could have like load-bearing walls for some parts of your house, and in other parts of your house, you might have columns and beams. And so, yes, you are allowed to mix your systems, and you will mix them according to your program and design concept. Those two criteria will guide you as to what will be the best mixture of your systems. And you can justify mixing your systems by mentioning your program and your design idea. So yeah, that's a really good question.
Okay, thank you, Tony. Now we move on to Shafa. Last question, please, Shafa.
Mr. Charleson. I would like to ask, so for our project this semester, we are told to design a house with growing house concept. So I think in a way it's basically a house that is not finished. So if I want my house to grow vertically, or if I want to add another story, how should I design the structure to prepare for the second floor? Or
Okay, that's a really great question. Now, let me just talk about gravity loads, because I haven't got on to the horizontal loads yet.
Yeah.
But in terms of gravity loads, what it would mean is that you would just make your columns a bit larger in cross section to accommodate the weight of additional floors. Okay, so if your columns typically for a two-story house were going to be like 20 centimeters by 20 centimeters, then if you were going to anticipate extra stories, you might make those columns 30 centimeters by 30 centimeters. And then you would have enough strength to add on those additional stories at a later date. But that's all you would need to do.
Okay. Is that clear, Shafa?
Yes, I would like to ask another question.
Okay.
What about the rough structure?
Yeah, well, the raft structure is a type of foundation system, isn't it? Yeah, and I guess that if I guess the raft structure for a two-story building will be shallower than the raft structure for, say, a four-story building. So yeah, that's a good point. You'd make your raft structure a bit deeper, knowing that one day you're going to add more weight to your superstructure. So exactly, you would strengthen your foundations a bit, and you would also make your columns or load-bearing walls a bit larger in cross-sectional area.
Okay, is that clear, Shafa?
Terima kasih. Thank you.
Okay, thank you, Shafa. Now, I think all the questions have been answered by Andrew. So now it's time for you to work for your own. Jadi kan kemarin, so Andrew, actually they haven't made the plans, not in that stage yet, but I have told them to prepare precedents so that they can learn from the precedents based on that, so they can draw it. Saya sudah bagi kalian di grup-grup, saya akan buka ininya. But before that, you will do the analysis or the drawing in Miro. So on that platform, so that we can see that you are working with your assignment at the moment and not leaving the class. So here we are. I will copy the link to the chat box so that we can visit, all the lecturers could visit your work. So here we are. You have 3 links: A in the class A, B in class B, and Q in class Q. So just visit those links and do your works. And then we have to visit the breakout rooms. I will break this room so you can go to your groups and discuss about the objects and then try to draw the structure. Jadi kalian gambar strukturnya di Miro tadi dengan preseden yang sudah kalian sepakati semalam, dibahas sekitar 30 menit. Nanti saya kasih timer di Mironya. Setelah 30 menit kalian kembali lagi ke sini untuk menerima kuliah yang selanjutnya tentang lateral load. Oke, saya akan buka ininya, roomnya. Nah, silakan kalian join. Yang belum ini, sebentar, saya joinkan. I think, please bear with me, Andrew. I am assigning my students to the group. So, it will take a little bit of time. Yang belum, wait. Q1 ini belum, siapa ini? Oke. Q6. A6. Okay. Yang bukan mahasiswa struktur kelas ini, salah, bukan mahasiswa struktur kelas arsitektur, kelas konstruksi dan struktur arsitektural, bisa ke other room ya. Itu biar kalian bisa diskusi di situ kalau misal ada pertanyaan seputar yang tadi sudah disampaikan oleh Andrew. Q5, oke. B5. Okay, oh, A6. That. Okay, I think all the students are in the breakout room, Andrew. So,
Cantilever.
wow, that's something new I learned.
So like
I
in
think
Wellington, you know, we have several buildings with cantilevers more than 7 meters.
7 meters.
I think our problem is in the contractor.
Pardon?
The problem
I
is
think the problem is that the civil engineer in Indonesia is always say that apa ya di bawah itu gitu.
So the civil engineers in Indonesia always mentions that it must not exceed 2 meters. So we cannot make those long cantilevers actually.
Well, look, that is ridiculous.
It's just for the house, or just on the deck or something, that there is no
No, for any building, house or commercial building.
Mm-hmm.
But, you know, if you have a long cantilever,
Uh-huh.
you must have a deep beam.
Yes, of course.
Yeah.
Mm-hmm.
But I mean, in theory, there's
Mhm.
nothing to stop you having a 20-meter cantilever,
Yeah.
but the beam will be very deep.
Yes. Of course. Oh.
So you must tell your civil engineers to
Mhm.
study some buildings from overseas.
Yeah, that's right. Okay.
Okay,
So-
thank you, Mr. Andrew.
Is there any more questions? Yeah, Bu Fardila?
Yeah. But for that long cantilever, is it allowed people to stay up there? Or
Of
just, of course.
Of course. The cantilever is designed for full gravity loads, for dead load and live load. And it is designed according to the concrete code of Indonesia, and it will be safe.
Okay. So we have to make a deep research maybe about materials.
Yeah, sure.
So
But
we're
there's
gonna
no-
have a
There is
We're not discussing.
there is no theoretical reason why you can't have a 20-meter cantilever.
Okay.
I just
need
suddenly flashback to the Bursa Effect building, you know.
Oh, right. So we have bad news. I think 2 years or 3 years ago, there's a building collapse in Indonesia. I mean, the floor
Cantilever.
slab is collapsed. Apa sih itu bursa stok itu? There's one building. I mean, inside there is a floor slab, and then suddenly when every employer of every staffs on those building going to that spot, and then suddenly it breaks down. So there is one news about those kind of building failure, I think about 3 years ago. So
There
Bu
were
Fadila
groups of people actually.
Yeah.
There were groups
Fadila
of
worried
people.
about that.
uh,
Fadila
groups of
worried
students.
about that because it's a cantilever, and then it's just break down because of
Okay.
too much people there.
Well, look, that's a design error,
Mhm.
because when you design a floor system, you must design for certain live loads. And those live loads, they include dense gatherings of people. So the designer obviously, the designer might have made a design mistake, or the contractor may not have built the structure according to the plans.
Mm. Right. Yeah.
Those are the two possibilities.
Mm-hmm.
But it's not a problem with the cantilever because there is no theoretical reason for limiting a cantilever to just 2 meters.
Yeah. Okay. Thank you, Andrew, for the new knowledge for us. Now, students are ready to go back and you can start your next session. I will bring them back. Wait a minute.
So will I share my screen again?
Yeah.
Okay.
Okay, I think everyone is.
Please tell me when I should share my screen.
Okay, wait a second. I think everyone is in the room. Adik-adik, apakah sudah kembali semuanya? Maaf, Musa.
Izin Bu, tadi ada
Iya.
teman saya yang terdisconnect.
Oh iya,
Ini-
nggak apa-apa. Ini sudah balik lagi kan ke kelas. Sekarang materi lagi. Okay, so I think everyone, please go out from your Miro and go back to this Zoom. Then we can. Oh wait a minute. Oh, stop. Okay. So now we will hear about the next lecture. It's about the lateral loads. So you can ask more about that because I know at the first session you have curious thought about the whole structure works, but here we learn it by doing it like several parts first, and then you can build up your understanding based on those parts. Now we continue to the next session. I will give the time to Andrew to start the lecture.
Okay, thank you, Fenty. So I'll share my screen with you all.
Yeah.
Okay, so now I'm moving on to the more difficult part of the structure of a building, and that is for it to resist horizontal loads like wind and earthquake. In Indonesia, your wind loads are not so serious, and so the big problem for you is to designing against earthquake. And I want to share this diagram with you that shows earthquakes in Indonesia for approximately the last 100 years. And you can see that you are living in a very dangerous country, aren't you? Look at all those earthquakes. And in the earthquakes that are colored red, Fenty, can you see my
Cursor?
cursor?
Yeah, I can see it.
Oh, thank you. So for each of the earthquakes that say are orange or red, those earthquakes would cause buildings to collapse. And I'm sure, you know, you are aware of some recent earthquakes in Indonesia that have caused many buildings to collapse. Like, for example, on Lombok and Palu, and in other areas of Indonesia. The only area in Indonesia that is quite safe for earthquakes is Kalimantan. But you know, Sumatra, Java, Bali, the Nusantara, Sulawesi, Irian Jaya, very seismic areas. And it's so important that we design our buildings so that they won't collapse in an earthquake. My own country, New Zealand, is also dangerous, we could say. It has earthquakes like, you know, Java, for example. So you live in a country that is very shaky. And every building you design, you must assume that one day it will have very strong shaking. And therefore, to stop it collapsing, you must apply the principles I am about to give you. They're quite simple, but they must be followed, otherwise your buildings will collapse. And so first of all, I'm going to look at the structural layout of the vertical elements in your building. And these principles I'm giving you, they are suitable for a two-story building. And mostly they're suitable for up to, say, a 10-story building. But first of all, I want to just talk about post and beam structures and load-bearing walls. Now, these two types of structure, they are very stable under vertical load. They're very good for resisting gravity load, post and beams and load-bearing walls. But unfortunately, if there is a horizontal load on these structures, they are very weak and will probably collapse. So we just have to be very careful when we use these systems in our buildings. Notice the load-bearing wall structure. If it has earthquake loads across the wall, it is very, very weak. However, if the earthquake shaking is parallel to the wall, then the wall can be very strong. So we just have to keep that fact in mind. Now, as architects, you have three structural systems that are suitable for resisting earthquake load. Just three. You have shear walls, which are the best system. You have braced frames, which are like triangulated frames. And finally, you have what we call moment frames, columns and beams, like a framework, moment frames. And so, as an architect, you have to choose one of these structural systems in each of the primary orthogonal directions in your building plan. And you can have as many elements as you need. So, for example, in this building here, I am using shear walls in both directions, in the X direction I've got 2 shear walls. And in the Y direction, these 2 walls. In this building, I've got braced frames. In this direction, I've got 2 braced frames there and there. And in the X direction, or say the Y direction, I've got a braced frame there and one here. And the same with my moment frames. In the direction along the building, I've got a moment frame here and one on the other side of the building. And in the in the Y direction here, I've got a moment frame here, which has got 2 bays. I've got a 1 bay frame here, a 1 bay frame here, and a 1 bay frame there. And so you as the designer have to choose one system in each direction. You could have shear walls in one direction and moment frames in the other. Or you could have moment frames in both directions. It's up to you. It depends on your program and your design idea. Now I'm going to talk briefly about each of these structural systems. This is the best structural system. It's potentially the strongest and the safest, shear walls. It's very important that the shear wall starts from a strong foundation and it rises continuously up to roof level. Most shear walls in the world are vertical, but it is possible to have them slightly inclined. Like, have you heard of the architect Zaha Hadid? Well, she would never use a boring shear wall like in my diagram. She never did a shear wall like that. All her shear walls are slightly inclined because she is so interested in communicating the idea of dynamic. Okay, so I'm showing you some very boring shear walls today, but I want you to transform them and make them more interesting according to your design idea. So this is the best shear wall here. It's got a strong foundation beam underneath it. The wall is continuous right up to the roof slab. And here are the floor slabs coming into it. We call it, maybe we'd call it a cantilevered shear wall because it cantilevers above the foundation beam. It's possible to have large openings in a shear wall like this. And in this case, we call it a coupled shear wall. And these are the coupling beams. And they require special diagonal reinforcement to stop them breaking in an earthquake. In countries like Indonesia, a very common type of shear wall that is used for housing, say up to 2 stories, is called confined masonry shear walls. And many houses in Indonesia rely on these types of shear wall for their earthquake resistance. And in confined masonry shear walls, the masons build the masonry wall and then the reinforced concrete columns are cast. And then the tie beams and the floor slab. Confined masonry walls are really good for low-rise construction to resist earthquake. Really good. And as I say, that is what is used in many houses in Indonesia. The alternative type of construction is to design reinforced concrete frames, beams and columns, and then after the concrete has hardened, after the concrete is set, then you come and put infills in, infill walls. Now, this type of construction is more dangerous because in an earthquake, the infills can fall out and kill people. And you see that many times after earthquakes. So this is what I recommend if you are going to use walls in your house, that you use confined masonry walls, shear walls. And this is a confined masonry wall. Here's your masonry, and here are your reinforced concrete columns. And here is your reinforced concrete tie beam. It's a bit like building a wall and confining it with a strong chain. Because the chain, it's like a gigantic sort of bandage tying your wall together and keeping it strong. So the tie columns and beams are absolutely essential. And so this is a very simple confined masonry house. Here is a tie column. Here's the tie beam and another tie column. And your masonry, it is actually load bearing for gravity. So the beam is not going to bend. It's there to help resist the earthquake forces. Because the weight of your floors will be taken through the masonry primarily. This is how, as I say, most Indonesian houses are designed. And so this is the section through the foundation. You call it, well, just the foundation beam. There might be a plinth beam. Here's a tie column with reinforcing bars with special sengkang or ties. Here's the next beam up here. But anyway, you don't need to worry about these details. This is not so important for design and construction, I don't think. And so after the walls have been laid, after the masonry has been laid, here are the concrete columns about to be cast. Here's the formwork for the column and the beams. And here is the floor slab will be poured across here. or the roof slab. Here's it's going to actually be, I think, a 4-storey confined masonry building. It's a university hostel building. There are tens of these buildings in India. And you can see the masonry, the reinforced concrete columns. Here the wall has been laid by the masons. All the bricks are there, and the next stage is to cast the column and the tie beam on the top. And so this is a very strong shear wall, okay, 3 stories high. And that will be effective in resisting earthquake forces, earthquake attack. Here's some buildings. Some of them, I think, are from Indonesia, actually. This is probably an Indonesian building. Here the bricks, a horizontal lintel tie, the tie column and the floor slab and tie beam at the top there. And so this is the type of construction, you know, that you will probably see if you visit a building site around Surabaya. That's my guess. But maybe you'll have some questions about that. Oh, this is an Indonesian house, Indonesia. This is Pakistan. And the others are from Pakistan. But this is an Indonesia house. The bricks, the confining members to create the shear walls. So in an earthquake, the earthquake will act at the floor levels mainly of a building. And so the earthquake shakes the building horizontally, and the shear wall resists the earthquake by forming diagonal compression struts like this in the wall. So during the earthquake force in this direction, pushing from left to right, inside the wall, there'll be this band of compression resisting the earthquake force. And at the same time, there'll be tension in this column. It'll actually go into tension just for those seconds during the shaking. And after the shaking, there won't be any tension in that column. It'll have some compression. And so the masonry wall transfers the earthquake force in compression down to the ground. And when the force is in the ground, the building will be safe. Now, if you are wanting to use a confined masonry shear wall, it's very important to have no opening, no windows, no doors in this particular shear wall. Otherwise, you cannot form the diagonal compression struts. So if you are wanting to use confined masonry shear walls in your building, some of your walls are not allowed to have any openings, any big openings like this. Just some of them. Many of your walls can have openings, but the walls that are to resist the earthquake, they must not have openings. Otherwise, they're too weak and they will break. Now, if you want more information about this, this is a very good poster for you. And it's in Bahasa Indonesia, as you can see. So you don't need to translate it. But this would be a very good reference for you. And maybe Bufenti can give you this reference if she gives you a PDF copy of my lecture. You can get that reference. But this is an example of confined masonry information, you know, in Bahasa Indonesia for Indonesian conditions. And another very good reference for you is found on this website, which gives you the principles of confined masonry construction. And if you want to be more confident about it, this is a very excellent book written for architects and for builders. It is not too technical for you. And you can download it or you can read it online at this website, the World Housing Encyclopedia, actually. So that's all I want to say about shear walls. I perhaps could say that for low-rise construction in Indonesia, confined masonry shear walls are very suitable. For medium-rise and high-rise construction, you should use reinforced concrete shear walls. They are a lot stronger. If you are building in wood, you could use plywood shear walls. And like in New Zealand and in California, many buildings use plywood or even gypsum plasterboard shear walls because the construction is so lightweight. Okay, the next system to resist earthquake is the braced frame. And here's the building with braced frames resisting earthquakes. The braced frame is based on triangulation. Okay, the elements must always form triangles, except that it is quite popular to use eccentrically braced frames, where we create structural fuses in these regions. And braced frames, they can be in any material, like this could be in timber or steel or reinforced concrete. I mean, it's quite difficult to make in concrete because the formwork is very difficult, but you can do it. This could be in concrete, this could be in concrete. And these ones, we need steel, tension only, steel rods, and these have to be in steel. So those are your braced frames. Now, finally, moment frames. This is where you resist your earthquake forces purely by a framework of columns and beams. And so each frame must have beams at each level, and you must have your columns, and at every joint connecting column to beam must be very strong and rigid. In other words, the opposite of flexible. Very strong and rigid joints. And so if you're using moment frames, this is what a frame looks like in plan. This frame is strong to resist earthquakes in this direction. So the column has to be wider in this direction. And here's the beam. So that is a 1 bay moment frame in plan, in concrete. In steel, it looks like that. There's your I column, your I beam, your I column. If you had your columns like this, for this moment frame, this would be a mistake, because in this direction, your columns are very weak in this direction. And so this would be a really bad design. And also for a steel frame, this is a very bad design, because your column is very weak in this direction. Like your column is strong in that direction, but weak in this direction. And so here is a typical simple concrete frame. This is your column. It has to be quite deep. It has to be deeper than a column that just resists gravity loads. Because in an earthquake, the forces on a column are a lot more serious than for gravity. So here's your column. Oh, sorry. Go back. Here's your beam in cross section. This is your beam connected to your floor slab. It's like a T beam, isn't it? That's your beam depth. That's got to be at least span divided by, say, 12 or 15. And here is your rigid beam column joint that has to be very strong with lots of reinforcing steel in it. And so if you are using moment frames in your building, you can choose to have as many frames and bays that you want. As many as you want to suit your design concept and your program. And to avoid the columns and beams becoming too large in cross section. And so this is your choice. There's an infinite number of options. I've just designed these two buildings to show you. Like in this building on the left, it's 1, 2, 3, 4 stories high, and then it's got a roof on top. In the Y direction, I've got just 2 frames. This frame here and this frame here. So they are strong in the Y direction. And each frame has 1, 2, 3, 4 bays. Okay, 4 bays. That suits my program and my concept. Now, in the X direction, I've chosen to use 2 shear walls. 2 concrete shear walls, 1 at each end of the building to suit my program. And then I did another design for the same building where I said, I'm going to have 2 frames in their Y direction, just 2 frames, but each frame is only going to be 2 bays long. And of course, that means I've only got like 3 columns now, whereas here I've got 5. So obviously these columns have to be bigger and the beams have to be deeper to make my frame strong. And so in this building, I've got 1 frame here. And because of the concept, I've got the other frame actually over here. It doesn't have to be opposite. It can be anywhere in plan. And I haven't shown on my drawing, I haven't shown the columns I need to resist the gravity loads to support my floor slabs. You know, there's probably a column here and another column here to support my floor slabs. But those columns just resist the gravity loads. In the Y direction, my 2 frames resist the earthquake forces. And in the X direction, once again, I'm using 2 concrete shear walls. These 2 shear walls, they could be anywhere in plan. They could be, you know, on the in the interior of the building, creating like a shear core, maybe. And so you as the architect, you have to decide where to place these structural elements. This is your decision. And then you take your design to the civil engineer and he or she will do accurate calculations as to the exact dimensions and how much reinforcing steel you need. But as the architect, you don't have to worry about such boring things like that. So just to summarize my first principle, the first principle of designing against earthquake is to have one structural system in each direction. We don't mix our systems. You don't have a shear wall parallel to a frame. That's like mixing colors and ending up with a mess of color. The next principle is that you must provide resistance in your building in the 2 orthogonal directions, the X and Y direction in plan. And so if you look at this, this graph here really, this is like the X direction of a building, and this is the Y direction. And the thing is that during an earthquake, the direction of earthquake shaking can come from any direction. We don't know. In 1 second, the building is shaking in one direction at one angle, and in the next second, it's shaking in a different direction. And so in order that our building can resist shaking from any direction, we must always provide resistance in the X direction and the Y direction. And so I've designed this really boring building here. Here's a plan. And so in the Y direction, the forces will be resisted by that shear wall and that shear wall. And in the X direction, by this shear wall and that shear wall. And these columns, which are very weak compared to the shear walls, these columns will just resist the gravity forces of the building. So this is the second principle. For your building that you are designing, you must have strength in the X direction and the Y direction. No excuses. Okay? Because if you don't have strength in one direction, the building will collapse in that direction. I can guarantee it. I've seen so many buildings throughout the world that have collapsed because the designers have not provided strength in both directions. The next principle is this. It's about torsion. During an earthquake, buildings will twist in plan during the shaking. Like, imagine my notebook as a building in plan. In plan, it will always experience some twisting or torsion. And so this principle is to prevent torsional problems. And that the principle is that first of all, actually, we need two structures in each direction. And so in this building, in the X direction, I've got a shear wall there and a shear wall there. I've got two. And they must be separated in plan so that they provide strong resistance against twisting. And so for the walls resisting forces in the Y direction, this wall here and this wall, it's separated in plan by that dimension. And so ideally, the best resistance for torsion is to have your walls or your frames on the perimeter of your building. That's the best option, but you don't have to do that. You can have them inside the building if you want to. It's your choice. But you must have some separation. Say, at least a quarter of the dimension of your building. That's a rule of thumb. At least a quarter of the dimension of your building plan. Well, sorry, I'll just go back. So those are really the main principles. But there's one question that you need to be asking me quite desperately, actually. And this is the question that each of you need to ask someone. You can't ask me because I would be too busy. So this is the question for you. How much structure do you need to resist earthquake? I've told you how to resist it using shear walls or braced frames or moment frames. But the tricky thing is, like, how many shear walls do you need? And how long do they need to be? This is the really difficult question. because it depends on lots of different factors, like how tall your building is, how heavy it is, whereabouts in Indonesia it is sited, what type of soil it's on. All these questions affect how much structure you need for your building. Now, the best way to answer the question is to use this rule of thumb software called Resist that you can download for free from this website. But if you haven't got any tutors to help you with the software, this software is very, very easy to use. I wrote it with a colleague for architects and architectural students like you. So there are no calculations needed. And so it is easy to use, but it's sometimes necessary to have some tutoring. And okay, there's a YouTube video you can watch, and there's also a step-by-step guide in the software to help you in the help section. So this is the best thing to use because you can fine-tune it for your building. You can design your house using the software, except it won't design confined masonry. It'll design reinforced masonry and concrete shear walls, but it will design concrete moment frames for you. But if you don't want to use that software, what you should do is to go to Mr. Ching's book again, and he gives some rules of thumb as to what the approximate sizes are and so on. And you might just have to use those and discuss them with your tutor. But I'm afraid to say they are rather inaccurate. But you've got to just do the best you can, and you've got to be able to say to your tutor, look, at least I've provided some resistance for earthquake. You know, I've got these shear walls in this direction and frames in the other direction, or whatever. And that might be the best that we can expect of you. But, you know, if you are very keen, then you certainly can use that software. And if you've got any questions, well, you'll just have to ask your tutors and see if they can help you. So that is the end of my lecture. And I'm sure that you will have some questions and comments to make. And now's a good time for us to have that time of Q&A. Thank you.
Okay, thank you, Andrew. That's very clear explanation. And thank you for keeping your pace, sorry, keeping your pace very slow for our students, because in this way they can understand you clearly. Because you, last time I think you worried that our student will not understand your English, but your pace is quite slow and they can understand very well about it. Okay.
Yes, but I do have a Kiwi accent.
Okay. So is there any questions? You can raise your hands like the previous session, and then you can ask the question directly or maybe comments. Okay, Shahla. Again? Yeah,
Okay.
please.
Hello, Mr. Andrew, I would like to ask more question about the for example of the confined masonry. In your slide there was this infill masonry, which are more it's dangerous because the infill can fall out and kill people. And I still don't understand the difference between the infill one with the concrete confining that surrounding the masonry, because yeah, I think it's probably the difference is the reinforced concrete, or yeah, I'm just still I just still don't understand what the difference, Mr. Andrew. Maybe
Okay.
yeah, the picture.
Okay, look, that's a really good question. I'm so pleased you asked that question. The differences in the method of construction.
Oh, okay.
Because you see, for confined masonry, you build your walls first, and then you cast your concrete columns. And so when you cast your concrete columns, the concrete can bond to your bricks very strongly. And so the bricks can't fall away from your column or beam because the concrete is, has got this really strong bond. But when you have your frame built first, then you construct your infill. You've only got a very weak connection between your brickwork and the concrete frame, because you've just got some mortar that is very weak, and when the building gets shaken in an earthquake, that mortar actually falls out, and it means that the infill can just fall into or out of the building.
Okay.
So look, that's a terrific question, and I hope I've made it a bit clearer for you.
Yeah, thank you. I'm probably mixed up with the end result. Yeah, thank you, Mr. Andrew.
That's right, because the end result is rather similar. Exactly. But the structures are very different and behave very differently.
Or we can see it like explicitly from the visual, like, oh, this one is confined while this one is infilled afterward. Yeah.
You can, as long as there's no plaster.
Thank you, Mr. Andrew.
Okay, thank you, Shahla. I think students get confused because they usually find the RC frame, actually the reinforced frame, like the left side of your image, Andrew. So they experienced that, but they didn't know that it's actually different between the confined masonry and the reinforced concrete frame. So they kind of find it difficult to differentiate between those two, because usually in Indonesia, in practice, we build our column first and then fill it with the masonry. Meanwhile, with the brick. Meanwhile, traditionally, they build together like your left image, like that. But in modern days, we find that the right side is the method to build it in our practice. So that's why they are a little bit confused, because it's actually almost like the same, but it's different on putting the elements, I think. Thank you for making clear for them.
But let me just add that if you are using confined masonry walls, you can use them as shear walls to resist earthquake. because the masonry is well confined with the concrete and the reinforcing steel. But if you are using infills, then you cannot rely on them to resist earthquake. And so if you want a building, say with lots and lots of windows everywhere and lots of openings, then you should use an RC frame solution. And because your RC frame will have to be strong for earthquake itself. And the RC frame will not rely on the infill to give it any strength. But if in your house, you have opportunity to have walls, some walls, at least 2 walls, without any openings, then they could be very good shear walls for you to resist your earthquake. And that means that the rest of your frames can be quite slender members because they only have to resist gravity loads.
Okay, thank you, Andrew. Next, we have Farrell. Sorry, Yuta. Okay.
Yes, Yuta, Miss.
Okay.
Thank you, Miss Fenty and Mr. Andrew. Earlier in the lecture, you said that we shouldn't be enslaved by the boring structure to satisfy the constructors. From my understanding, there is no limitation to imagination, right? And then, but there's a limitation in making it a reality, such as economical limitation. What I want to ask is, what part of the structures that we can change or adjust to fulfill the economical limitation while still making it a strong structure and expressing our concept and ideas? Thank you.
Well, I mean, you have to look at your design brief. Like, I mean, while you're in a school of architecture, my opinion is that you shouldn't need to worry about the cost of your building. You know, during your time in the School of Architecture, it's about ideas. And as you said, there's no limit to ideas. And so you should be brave and push yourself to express your design concept and to create maybe an innovative program, you know, spatial layout for your design. And then having done that, then you bring in your structure to provide structure for gravity loads and for lateral loads. And don't, you know, in my opinion, you don't need to worry too much about the economy of your building, because you have to, unless that is part of what your lecturers have asked you to do. And if your lecturers have a stressing economy, then I'm very sad to say that you will have to produce a very boring building. You will have to produce a building that is cheap to construct, and that will mean a rectangular or a square grid of columns. It'll mean, you know, that everything will have to be really basic and simple. And so, sadly, I mean, it's a bit like motor cars, isn't it? If you want an interesting motor car, you know, you can't buy the cheapest. You can't buy, you know, the very basic vehicle. But if you want something with more design flair and design excellence, well, then you have to pay a bit more money, and in order to get something with that better quality. And architecture is just like that. So I think that's about all I can say. There's no easy answer.
Okay, Yuta.
Okay, thank you, Mr. N.
Okay, thank you, Yuta. And next we have Kalista.
Yes. Hi. Thank you, Ms. Fenty, for the opportunity. Hi, Mr. Andrew. I have a question. Previously, you say about how confined masonry wall can't have any opening because the compression system. Is it the same with the load-bearing walls? Do they have the same compression system, or because load-bearing wall refers to gravitational forces and the masonry wall refers to lateral forces? They have different system. Yeah, I guess. Thank you.
Thank you. Once again, a very, very good question. If you've got a load-bearing wall, for gravity loads, it can have openings, and above the top of each opening, there must be a lintel beam. Fenty, what's the Indonesian word for lintel beam?
Balok latai adik-adik. Ingat nggak balok latai? Jangan-jangan mereka lupa. I think they forgot those thing. Jadi kalau di atas jendela ada baloknya, nah itu lintel beams, itu namanya lintel beams.
And so if you have a load-bearing wall, yes, sure, you can have openings in it, like windows and doors, but above each opening, as I say, there must be a reinforced concrete lintel beam to transfer the gravity loads from above the opening around to the walls on either side of the opening. Now, if you want that load-bearing wall to function as a shear wall, then it's different. You cannot have those big openings because you will destroy the diagonal compression strut. So if you are wanting to use confined masonry walls in your house, what you would do is in each direction, you would choose, say, 2 walls that are like parallel and separated in plan. And those walls would have no openings. And they would be the 2 walls to resist the earthquake forces for you in that direction. And then all your other walls, they could have many openings. You know, they could have total openings because you're not expecting them to help with earthquake. The other walls could in fact be beams and columns. Their job is just to resist gravity. And so in your house, in one direction, you would have a minimum of 2 walls, 2 walls, say, in the Y direction, and 2 walls in the X direction, anywhere in plan, as long as they're separated. And then, as I say, all your other walls can have as many penetrations as you want. Totally glazed, if you want. No problem. Thank you.
Oke, thank you Andrew. Sudah jelas ya tadi, siapa tadi yang nanya ya tadi? Aduh, udah hilang namanya.
Kalista.
Oh ya, Kalista. Ya, thank you Andrew.
Yes,
Okay.
thank you.
Okay, is there any questions from other students before we move on? Should they present their works in front of you, Andrew? I mean, just a sample, or I think because actually the this task will be presented next week in front of all the tutors. So you don't have to check their works one by one because after this is already, the lecture is already finished actually. And after this, they can work by themselves with all of the lecture from you. I think if I got the PDF from your presentation, then they can work with their assignment as well. So,
oh, great. That's great.
Yeah. What time is it in New Zealand, Andrew, actually?
It's almost 10 p.m.
Oh, sorry for that. Okay.
It's almost my bedtime.
Yeah.
Okay.
That's what I'm worried about. So yeah, I think if there is no more questions, I think we should finish our lectures here. Thank you for Andrew for coming to this lecture, and I think we will meet again 2 weeks from now. I think 3 weeks from now. I forgot the schedule, but
Yeah, that's right.
Next meeting with Andrew, you will learn about high-rise building. So the concept of the structure to use in high-rise building. And today the lecture is about the basics of the structure, and then you can do your homework to present it in front of all the tutors based on your class next week. So yeah, I think, I will explain a little bit in Indonesia, I think, Andrew. Sorry for that. Jadi absennya nanti silakan ditanyakan ke koordinator masing-masing untuk kodenya untuk absen jika belum di absen. Kemudian tugasnya akan diluncurkan nanti melalui classroom. Kalian bisa melihatnya dan dianalisanya berdasarkan apa yang sudah dijelaskan oleh Andrew pada hari ini. Gitu. Jadi silakan nanti dicek classroomnya di malam hari. Kami akan mengupload tugasnya di sana. Dan adik-adik bisa bekerja sesuai dengan apa yang sudah dijelaskan tadi. Terima kasih. I think thank you for all for coming to the class and thank you for your participation. I'm really glad that you are very active on this class, even though we have sit in front of the laptop from the morning. But I know that you are very enthusiastic in this class. Thank you for that. And then you can continue your work in Miro. You can access it all time. And then you can work together with that and finish your homework and then submit it to the classroom. Thank you again, Andrew. And I think good night for you. Sorry for bothering your bedtime. Department of Architecture, really glad to have you and see you next meeting, Andrew.
Thank you very much. I've enjoyed speaking to your students. And students, just remember, apply those few principles to your designs. I'll see you in a few weeks' time. Goodbye.
Bye-bye, Andrew.
Bye, Andrew. Thank you.
Thank you.
Bye. Thank you.
Thank
Bye-bye.
you.
Bye.
Okay, I will end the meeting now. I will contact you through email, Andrew, for the continuation of this project.
Sure, Fenty. Thank you for your management of this evening. It's gone very well. Thank you.
Okay, thank you, Andrew. Bye, Andrew.
Bye.